In this video, you'll learn how the expression for elastic strain energy derived in the previous video can be used to form the beam element stiffness matrix. Recall from the previous video that the elastic strain energy for a beam element is given by the following expression. Lambda E is equal to E times by I divided by 2 times by the integral from 0 to the length of the element of d2v by dx squared all squared dx. d2v by dx squared is the curvature of the beam. Also recall that Vx in this expression here was previously derived as the following. V of x is equal to a matrix of shape functions n2i minus 1, n2i, n2j minus 1, n2j, multiplied by the vector of element displacements ue. This can also be written as n times by ue, where n is a matrix containing the shape functions. We can differentiate this term by term to get our expression for the strain energy. Working with d2v by dx squared, we get the following. d2v by dx squared is equal to d2 of the matrix n by dx squared multiplied by the vector ue, which is equal to term by term d2 n2i minus 1 by dx squared d2 n2i by dx squared d2 n2j minus 1 by dx squared d2 n2j by dx squared multiplied by ue. We differentiate the shape functions n with respect to dx and not ue because ue is not a function of x, whereas as we showed before, the shape functions are functions of x. We can rewrite this as b1, b2, b3, b4 times by ue, the vector. b1, 2, 3 and 4 are just simply notation that we have assigned to these second derivatives of the shape functions. As a result of this, we can also write d2v by dx squared is equal to b times by ue. Then, going back to our expression for strain energy, we need to square this term. So, d2v by dx squared, all squared, is equal to b times by ue, all squared. And if we expand this out, we get ue transpose b transpose b ue. So, our expression for elastic strain energy for a beam element is now given by lambda E equal to EI over 2 times by the integral of UE transpose B transpose B UE integrated with respect to dx, or rewritten half times by UE transpose times by EI B transpose B dx times by UE. In our previous video lectures, we showed that the strain energy can be written in the following general form. Lambda E is equal to half times by UE times by a matrix A times by UE. And it was shown that the matrix A is in fact the element stiffness matrix. By inspecting equation 6, we can then say that A, in this case, is just given by EI integral of 0 to L B transpose B dx, which we will call the element stiffness matrix. You can clearly see here in this expression in equation 6 that although this features an integral sign and some constants, we have two matrices which form a square matrix because there's the transpose of a matrix times by a matrix, and this is essentially equivalent to our matrix A. We can clearly now see that matrix A is in fact the stiffness matrix. Generally, this is evaluated by numerical integration, but in this course we can perform analytical integration because the expressions for B are quite simple. Overall, the element stiffness matrix will look like this: EI times the integral of the matrix elements, so B1 squared, B1, B2, B1, B3, B1, B4, B2, B1, B2 squared, B2, B3, B2, B4, B3, B1, B3 times by B2, B3 squared, B3 times by B4, B4 times by B1, B4, B2, B4, B3, and B4 squared. And that's all integrated with respect to dx. As an example calculation, we can evaluate one of these elements. So let us evaluate the integral of B1, B2. So that gives us the integral of d2n2i minus 1 by dx squared. So we can see that b1, as we showed earlier, is d2n2i minus 1 by dx squared, and our second term b2 is d2n2i by dx squared. So we'll also write that d2n2i by dx squared, all integrated with respect to dx. If we just perform these differentiations on our shape functions that we derived last time, we get d2n2i by dx squared equal to minus 6 over L plus 12x over L cubed, and d2n2i by dx squared is equal to minus 4 over L plus 6x over L squared. Putting all this together, we get the integral of b1, b2 with respect to dx is equal to 12 times 0 to L 2 over L cubed minus 7x over L4 plus 6x squared over L5 with respect to dx, and that's just equal to 6 over L squared. Performing all of these integrations, so all 16 of them, we would get the full stiffness matrix in analytical form, which is just EI over L cubed with elements 12, 6L, minus 12, 6L, 6L, 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L, 4L squared.